about this too.
Cool.
Go ahead.
All right. Thanks for the introduction and thanks for inviting me back. As you can see, I've been here in 2018. I'm wearing the exact same shirt. It's Rogero's there, Ricardo's there. So that was pre LSST being kind of real. And now we have LSST starting commissioning, and that will be a lot of what I'm going to talk about today. So my talk will have a lot of data, less kind of theoretical, more data driven. And of course, like stop me if you have any questions. All right, so that's my start. Okay, so what happened between these two pictures? A lot has happened. If you really think about it, 2018, 2024, DES results came out. Year 3 results came out, both 3x2 point and 6x2 point, and supernova for year 5 came out. This whole DESI evolving dark energy thing started, and more H0 measurements happened during that time. There are, of course, other big cosmology news I didn't add on here, things like parity violation and other things. So there's been a lot of things that happened together with all the data that's gotten collected and processed and analyzed. What I'm going to talk about today and like focus on is one of the things, which is Rubin during that time became a real thing. It was pretty real at 2018 already, but during that time, as you can see, this is kind of the dome getting built, the secondary mirror being installed, commission. The first on-sky image taken from the commissioning camera happened about a month ago. This was the celebratory kind of night. And it has been taking data since then. So there is like real-time LSST data coming in, not LSST, kind of Rubin data coming in like every night. And people who are in commissioning, which maybe some of you are, can actually go look at the images and find stars and galaxies and streaks and artifacts and other things. But this is now real. LSST real camera, so the LSST cam will be up in a month or so. And then there will be some commissioning, and then it actually is going to start the survey. So maybe to put things in more quantitative terms, this is the timeline that's in this website that hasn't changed for a while, so it's probably not going to slip too much more. What you can see is, so we're here. We're in the kind of beginning of this data preview period. So what is shown here is the timelines for things releasing to the public. So this is everyone. I think everybody in Brazil, is that correct? Sure. Everybody in Brazil and US can access this data. So we are currently in this orange band of DP1, data preview 1, which will be some of these initial commissioning data, not on the full camera, just on the smaller camera. And then the system for lights is the first time the LSST cam, the huge like 10 square degrees camera is going to get first light, and then start of operation. That's when the first kind of the first year LSST actually starts. So after that, data preview 2 is 6 months of data. That will be the first big chunk of probably cosmology grade data coming out of Rubin. And you can see where you're accessing it is whatever, end of 2025. Okay, so this is all really happening. Lots of things are being very exciting. Okay, so data's around the corner. Are we ready to process it? So if you think about it, we're just finishing up DES, where the last data was taken in 2019. So it takes a long time to process. You're never getting what you expect to get. So saying what you're ready is kind of fooling yourself. So we're never ready. But it's okay. Ready really just means that we have the tools or have the flexibility to deal with what's going to come. And expecting kind of the mental preparation of it's not going to be smooth sailing is part of getting ready. Okay, so with that, this is sort of what I'm going to talk about today. I was told, or I was given the topic of talking about LSST and perhaps more focusing on the desk kind of mindset. So I'm going to talk about the static science within LSST as operated by desk. And then I will go through some of the lessons learned either from simulations or stage 3 surveys. There was a lot of discussion on Scott's talks already about beyond 3x2 points, so I'll keep that part short. We can leave it for the discussions, and I'll go some future directions. I'll spend most of the time actually looking at what we can learn from stage 3 data. There's a lot we can learn from simulations, but really data, I think, is where kind of all the hard lessons are learned. Okay, so what do I mean by static science? I mean things that don't blink or move. So supernova is not static science, transient stuff, planets, that's not static science. So basically we mean large scale structure. We mean mapping the structure of the universe from dark matter, which has sensitivity of the cosmological model, right? So that positive cosmological model, we can map it using different things. Galaxy clusters, galaxies, weak lensing is what you can get from LSST and other optical imaging surveys. But also beyond that, you can use CMB experiments, scientific mapping, spectroscopic surveys, so on. So what we want to do is this, right? We want to map this dark matter evolution over time and the structure itself. Okay, so what do you learn? You learn fundamental physics about dark energy, dark matter, gravity, inflation. This, again, Scott talked about some of that. You learn some, maybe not as fundamental physics, but also important physics, astrophysics about parametric feedback, intrinsic alignment, galaxy halo connections, and hopefully also physics. Okay, so how does using galaxies and lensing tell us about static science? So very simply, galaxies trace dark matter. So the structure of where galaxies distribute should be a proxy for that with some bias parameter. And the way galaxies align, because how light deflects off of dark matter, there is some alignment that's related to that. So this is how predominantly how LSST desk thinks about static science. There might be other people thinking about it in different ways, but in the desk framework, this is what we're talking about. And just in case people are not familiar, Rubin Observatory is the project. Desk is one of 8 science collaborations. There's 7 more that people don't know a lot about. There's galaxies, there's transients, there's strong lensing, I think. So there's other things, but Desk is the one that is dark energy focus and the biggest one. Okay, so from this, we have decided in Desk that at the very least, we'll do these things. Okay, so these are the 3x2 point functions and galaxy cluster counts cosmology. So again, Scott talked about this a little bit. Basically, we want to look at 2-point correlation functions. So this is just the Gaussian information of galaxy clustering, galaxy shear cross correlation. So this is the galaxy lensing Scott showed, and then shear. That's like cosmic shear, psi plus and minus. Okay, so that's a set of 2-point functions. And then there's other things like you can find clustering of clusters and just count them. So that's 1, that's 2, that's 3. And then you can, by mapping out how many clusters there are as a function of mass and redshift, that has sensitivity to cosmology. Okay, so in Desk, you sort of decided this is the baseline we're going to do. And I just want to quickly introduce this. In order to get ourselves organized, we started this kind of initiative called STAR, Static Analysis Roundtable. So it's modeled off the way DES does the key project. So it's just a venue where all the working groups can talk together, and we build these step-by-step pipelines to do redshift, do shear calibration, so on and so on. So this started about 2021, and the focus has been on both testing on simulations and precursor data. What I'm going to talk about later kind of largely falls under this umbrella. Okay, this is not a very interesting chart, but I'll show it anyway. So this is a flow chart of how data is going to flow. Okay, again, emphasizing that we are different from DES, right? So the main difference of Desk versus DES is Desk doesn't own the data. The data is owned by Rubin. So there's a difference between the gray part that is Rubin and the yellow part that's Desk. So we take the data release and we do stuff after that. And then it's broken down into different elements where people are actively working on things. So mostly I give you an impression that we're organized, things are happening, and many of you are involved in many of these components. Okay, so with that set up, I'm going to quickly kind of flash by a couple of things we got from simulations. So the kind of first 3x2 point end-to-end analysis from desk is probably going to go to this paper led by Judy Pratt, who is a former postdoc at Chicago. So what she did was she just basically tested the pipeline. Okay, the bare bone pipeline, if I just take galaxies and shear that look like what we expect for LSST galaxy and shear with no systematics, like everything bare bone, can I recover cosmology? That seems like a reasonable question to ask. So she tested both on a Gaussian simulation, which is like very simplistic. You better get that right, otherwise we're in trouble. And then Cosmology DC2, which is a slightly more complicated mock galaxy catalog. The redshifts are, again, very idealistic. And just plugged it in, ran measurements, made covariances, ran cosmology, and turns out we can recover cosmology. So that's good. So this is mostly a pipeline test, right? So before you do anything complicated, this probably should work. And it serves as a baseline to kind of build on top to kind of complicate each of the components as we go along. This is showing that we're doing both real space and harmonic space. And this is kind of a W naught WA situation. Okay, so the goal is, okay, we start from here, and now let's start making every part of this a bit more complicated until it becomes data-like, and then we're done. Okay, on a similar angle, the cluster group also has been doing something along that direction. So this is going through the package called CLMM, Cluster Weak Lensing Mass Modeling Library. Michelle's going to be here. He is not going to be here.
Michelle, yeah.
Okay, so you can't go talk to him.
Sorry.
But unfortunately, I also don't know the answers. But this is like to get mass model. So you have a bunch of clusters, you want to model a mass. So this is showing kind of the shear profile of the cluster, and this is recovering the mass observable relation. So again, this is first step, very simple things, it better work. Okay, so that's really how I want, like, as much as I want to talk about simulations, I'm going to spend most of my time in the stage 3 data part. Okay, before I go on, any questions? Actually? Yeah.
This is a Layson simulation. I mean, I don't know if you will touch on this, but how do you separate the transient effect from the static effect?
Yeah.
And how many data, how many nights, let's say,
Yeah.
data you need to have to do this analysis, or for example, this simulation, how many,
Like the computational costs. You mean the analysis, how long did it take?
Yeah, no, sorry, the simulation, how many nights, let's say.
Am I simulating?
Data it represent.
Okay.
Without the simulated study.
Okay, so answer your first question. So the static and the transient science kind of are going in two different pipelines. So the transient people mostly care about from different times we revisit the same sky if anything is moving. So the core of their data processing is a differential imaging. So this to the next, you differentiate it, is there anything left? So they go in a completely different direction. So the static science, we just accumulate, right? We just add until it gets.
And the transients are noise for you, or you try?
Yeah, it's noise for us. So there are things come and go. They mostly would just average out. So if they're faint enough, if they only, right. So if there are things appear in one frame and the other frame, we actually flag it and don't count it, right? So cosmic rays, for example, they're masked out. So it is kind of an opposite, like our junk is their thing, kind of, yeah. So that's the first one. The second one, so the thing we're simulating is year 1. So yeah, so year 1, this is what we're simulating. The rationale is like, we should probably make sure we can do year 1. Like year 10 is a whole different. Yeah. Okay. So switching gears now. Stage 3. Okay. So what have we learned from stage 3? So there is more than one way we should extract lesson learned from stage 3. The first most important one is just we did stage 3, right? It has been done. There's lots of papers being written. Most of the answers are probably there. So I think that's something I feel like people often forget, that a lot of things are actually already done, and it's important to preserve that knowledge to LSST. So that's one. Independent reanalysis of cosmology is important. So a different group doing the same analysis with the same data comes up with different answers. So the first line is showing kind of collaborations analyzing each other's data. So kids analyzing data, DS data, DS analyzing kids data, and so on. The second one is desk kind of reanalyzing other people's data. So I will talk a little bit about this since I was mostly involved in that. The third bullet point is, okay, so we know how to do cosmology, but we also know there's so many steps before cosmology that become the catalog we use. The last step is actually relatively simple. You just take a bunch of already clean catalog, do a bunch of two-point functions, and then run some MCNC chain. There's a lot of work going into producing that catalog, and we really never talk about it that much. So that is kind of going one step upstream and asking, would we still get a robust kind of catalog if we do some different tests? So that's work done by Marika in 2018, and I'm going to present one of the work we're doing now. And the last one I want to sort of semi-advertise to look kind of beyond the stage 3, the 3 big stage 3 experiments. There are other data out there too, and we can learn something from there too. Okay, so as I said, I'm going to talk about these two. And again, interrupt me if I talk too fast. Okay, so I think I don't need to repeat what stage 3 found. Stage 3 is not done yet, but up to this point, this is sort of the summary last from HSC in their 2023 paper. So status is like this. They're all sort of similar constraining power in SA. They're all sort of lower than Planck. Okay, so a couple things I want to note. One is we all publish results, but they're all like small things we never fully figured out. So in DES, we never fully figured out what X-lens is. In HSC, the last spin has always been a bit weird in Redshift. So it's not closed and done, and I think it's something to remember that like it's not like we publish a paper and we never talk about it. There's a lot more things we can probably learn from it. The second point is just these collaborations are phenomenal, right? There are like 100 people trying to do one thing. How can you imagine that? So like the communication and the organization between the people is a big part of it. Scott has a lot of experience in this. You can talk about that. And I think that's another important part that we need to preserve and move on to desk. And yeah, the last is just the advertise that year 6 should be out next year. Similar time scale for the last HSC and kids results, and that would be basically the conclusion of stage 3 before we start serious Rubin analysis. Okay, I'm going to flash a couple of these reanalysis projects we've done in desk. So the first one is actually how Scott got me to work in desk. So we had a workshop in Fermilab, and he introduced me to this project, and then we started doing it, and here it is. This is also the project I talked about in 2018 when I was visiting here. So this is reanalyzing deep learning surveys, CFHLens, DSSV, and kids 450. So you can think about it sort of like stage 2. And the lesson was interesting. It's like, okay, if you read all the papers and you put everything on a plot, you will sort of think they're all agreeing. But if you actually reanalyze everything using a consistent framework, you will find that they're not actually agreeing. Important lessons are analysis choices do matter. It's not like we're all making the optimal analysis choice for each of the data sets, but if you do make the same thing, they can get different results. This was also a good sort of wake-up call, and the wake-up call is a strong word. It's a good kind of lesson about blinding. So there is the reason that maybe none of these were blind, I think. Was SV blind? Does anybody remember?
Kids was blind.
Kids was blind, so SV was not blind. Yeah, so I think some of that perhaps is due to kind of confirmation bias, where people thinking, oh, SA cannot be 1. That's no way. So they moved it down. So anyway, so that's that. The kind of the follow-up of that was this work done by Emily Phillips Lumley, who's a grad student at Duke, who reanalyzed kind of the next version of it, and people tend to agree a lot more. There's still kind of small shifts if you think can kind of look at the yellow kind of shifted a bit, but all within sort of reasonable amounts. And yeah, so I think the lesson there was like we start to argue about smaller details about things shifting around. And then I think there was a big thing about doing log AS or not log AS will change something. But there's some kind of slightly less kind of serious messages over here. And this is an ongoing work from David Sanchez Cid in Desk, doing HSC 3x2 point. So what is interesting here is they're actually doing something new. They're not just reanalyzing. They're doing galaxy clustering, which has been done. Sorry, this is cosmic share. Cosmic share, which has been done, galaxy clustering, which has been done, but they added galaxy lensing and did a cosmology with it. So this is in some sort of review in Desk, and hopefully it'll be out soon, but also a way to test the pipeline and produce interesting results. Okay, Anna's not here, but Ami is here. So the Kids plus Des kind of analysis is kind of a joint collaboration effort. So yeah, so I think that was an interesting experience. They can tell you more of kind of trying to actually understand what each other are doing. So when we live in a collaboration, you tend to get a little brainwashed, and then you just like think this is the only right way to do things. But once you open up the world and talk to somebody else, they'll tell you, no, that's not the right way. Anyway. So point being, that was a good exercise, and basically they came out with some kind of optimal between the two collaboration constraints over there. Okay, so okay, so that's sort of a very quick rundown of the reanalysis that has been done. The next one I'm going to talk about is something we're currently working on. So this idea of there's so much happening before a shared catalog exists. Have we ever looked at that part and see if they're legit? So this is a reanalysis of kind of the diagnostic tests before producing the shared catalog. This part is a little technical, so I apologize for that, but I'll talk about it anyway. So this is done by Jasmine, or grad student at Chicago, and Yuki, a research scientist at Chicago. And we're looking at these three data sets, the ES and HSE are 3 and kids 1000. Okay. Okay, so a bit background. So right, so we measure shear from galaxies, right? So usually if you read a shear catalog paper, most of the paper is about tests. So we do this, we don't find anything, we do that, we don't find anything, we do everything, and we don't find anything. Therefore, this is ready, you can do science with it. So that's kind of the state of the affair. These tests, they kind of accumulate. So I'm putting here the first detection paper of cosmic shear in year 2000 from David Bacon. So they had like 1 or 2 tests. So they plotted shear as a function of PSF ellipticity. And they found a correlation for low signal to noise galaxies, and no correlation for high signal to noise galaxies. So therefore, they decided this is not supposed to happen, right? The shear of a galaxy should not depend on what the PSF looks like. So this data is not good, this data is good, so we do cosmology with this. So this is kind of the beginning, the birth of these tests. As time moved on, people start to add more and more things, and now it's sort of its own industry, that there's just like a list of never-ending tests that you need to do in order to believe your catalog. Okay, so the goal of this project is to build a pipeline within Desk that does these tests and reproduce what has been published if we can. And then to unify and do a set across all of them to see if they still pass all the tests or if anyone fails because they didn't do another test, because they're not actually homogeneous. And the main goal is to, okay, compile this knowledge and come up with some proposal or recommendation from what we need to do for LSST.
So Chihway, you
Yeah.
take the catalogs, the sheer catalogs from these
Yeah.
operations, not image catalogs.
No,
Try to
yeah.
measure
So
sheer.
somebody can do the next level of doing images to catalog.
Okay,
I think somebody is thinking about that for HSC, but it's a lot of work.
because they have different methods, right?
Yeah, to measure the thing and yeah, it's like, yeah, it's just a lot of like IO problems, like reading in the spit data format is a different, yeah, anyway. Okay, so here's a nice table compiled by Jasmine showing, this is not all the tests, but it's the tests we're going to do in this paper. So they go into kind of just general looking at the PSF, 1-point functions, shear as a function of something, something as a function of something, and 2-point statistics tests. So like broadly, you can see, okay, they're not all doing the same thing. A lot of people are missing some things. It's a little bit DS-centric, but there's that. B, even if I say like this is a row stats, they may not actually be doing the same thing either. So different choices of what covariance you use, different choices of where you cut the scales. Actually, everybody's doing something slightly different. But everybody concluded that they pass this. So that's that. I think it's important to notice that and kind of re-examine the way we do these tests.
So passing the test means that the cosmology is the same. Is that
So so these, okay, I will mention this later, but a lot of these tests, it's very hard to connect directly to cosmology, right? So it's heuristics. It's like, okay, we know shear should not correlate with PSF size, and it does. So that's a problem. So we go look at the data again and maybe do some cuts and whatever and see if it works. So usually that happens before any cosmology happens. So usually like there's not that much you can do aside from if there's actually a bug. The most you can do is make cuts or make masks or something.
cosmology is at the very end?
Cosmology, like these are marginally, like these B modes and like Turostat, Falsat, you can sort of connect it. Meaning like if you detected something, that means that will bias your cosmology some amount. But most of them are hard to connect, yes.
All of the catalogs have all the ancillary defined lesion you need, like PSF,
Yeah.
visual stars, focal point.
Very good question. So we had to fish for a lot of them. It was very hard. And there's still a long list left off that we couldn't recover. Even for I'm in DES, there is a plot in Teams that can't reproduce. I asked Joe, where's this data? Joe was like, it's probably in a tape somewhere. So yeah, so this is another lesson learned that I'll mention.
I have a question.
Yeah? Go.
Have you studied if these tests are redundant? So is it possible to pass, for example, all the DS tests and fail at the kids only tests?
Yeah, they are like a lot of them are related, but a bit redundant. So a lot of these galaxy shear versus something is somewhat redundant to the row stats and tau stats things. Yeah, and as I said, it's like because some of the tests are heuristics, you don't. There's no direct connection to cosmology, so the passing failing is a bit shaky anyway. But yeah, it is totally possible, and I will show examples that people don't pass some of these uncharted. So the check mark is things that were done in the paper. So if they don't pass in some of these, that means that they passed on some tests and didn't pass some tests. That makes sense. Okay. Okay, so we're gonna run down some plots and just one plot to orient you. So I'm gonna label kids in green, DS in red, and HSC in blue. This is just looking at the PSF. So on the left is the E1 and E2 of PSF and the size of the PSF. First time I made this plot, I thought I made it wrong because the HSC PSF size doesn't overlap with the DS PSF size. That means like the DS image quality is that much worse than HSC. But this is actually real. So HSC image quality is a lot better than DS, and kids is sort of in the middle. the PSF itself, you can see, for example, the blue is more negative. So they don't need to be centered in 0, and they are not. And that's just a function of the optics. So the optics naturally produces PSF that are asymmetric or whatever, and they show up in these plots. The important thing is whether you can model it. So this on the right is the residual after modeling. And then you can see that they're more centered on 0. Okay, so this mostly tells you what the data looks like, which is an important thing to know, and how good your PSF model is, which is another good thing to know.
What is TPSF? What is that? The last one.
This one?
Yeah.
So it's the error on the PSF model over, so fractional error on the PSF model.
No, the T. It is the size. The size. Okay. Good.
Oh, T, yeah, T is size. Sorry. T is size. Sorry about that.
Model for is the same for all the students?
No, they all have their own way of doing it.
Those parameters are characterized in this.
So the E1, E2, and T are on the same units, but the way people go about to model them are different. But so that this is comparable on this plot. But yeah, the how they got to here is not uniform. Okay, so that's good to know. You can also look at the galaxy sample. So this is the galaxy sample that went into the shear measurement. So this is the cosmology sample. I'm showing shear 1, shear 2. This is a bit redundant from the previous plot. This is the galaxy size. This is the galaxy size ratio. So size over PSF size, signal to noise. So you can see some sharp things that indicate how they created the sample. So somebody must have put a cut there. So you can see, interestingly, kids didn't put a cut in the size. And that also shows up here. The size, the green histogram goes to much lower. You can also see indications of the ellipticity having a bump there in the blue and the green. So those are people putting cuts on the ellipticity himself. So that is allowed, and that shows up here as a feature. You can also see, like, yeah, kids goes to much lower signal to noise. The interesting thing is HSC, actually they cut pretty aggressively because they have too many galaxies and they start blending to each other. So they are actually overly conservative in selecting their galaxies. Yeah, so like these plots, they don't like tell you pass or fail, but I think it's interesting to stare at just to sort of understand the character of your data and how the different data sets are quite different when we look into them. Okay, so this is the mean shear versus something. This is like David Bacon made this plot, whatever, 24 years ago, in the first kind of analysis, and this is our new version of it. So what you are looking for here is a reasonably flat line, because shear should not be a function. You shouldn't have more shear when you have a higher signal noise, or more shear when you have a rounder PSF. So these things should all be sort of flat, and then if we fit a line, we evaluate how flat the line is. There are interesting things like here. This, I mean, they never made this plot, so they wouldn't have known, but like there are some features in this plot that a flat line wouldn't really show you much, but they definitely show up as interesting features. What could this be? This could be a shear calibration issue. It may or may not matter for cosmology, but it could be in the data. Yeah, there are other things. Yeah. So, okay, I don't have that plot here. Okay. Row statistics. So it's a slightly complicated thing to explain, but it's a 2-point function of the ellipticity errors or the PSF errors. So, right, so like this was the 1-point function on the right. And then this is, okay, to see if those errors have any spatial structures, and they should, because the PSF is a spatial thing, like it is the focal plane geometry. So yeah, not too much to say here, just like DES has usually a lower and flatter line, where our PSF model is a bit better, but also our focal plane is bigger. So the characteristic feature where it turns over is related to how big your focal plane is. And then there are different things you can spot here. HSC is usually a bit higher. than others. One thing about HSC is because their seeing is so good, the ellipticity actually is bigger. And that's not their fault. Like, it doesn't matter for sheer, but like, it shows up more on these plots and yeah.
Yeah, can you go to the, yes, no, the previous one.
Yeah.
It's just a question because they probably, the data that you get is already multiplied by these weights that take into account the systematic effects on PSF.
So we're different, like, so the shear weights are only a function of signal noise and size. So they're just a statistical thing. We're not like large scale structure that we have weights that correct for things. Okay, so this is the one plot we can make to ask how much of this propagates into cosmology. So the way you do it is you cross-correlate these PSF quantities with shear, form another 6 two-point functions, and do some linear fitting. So this is sort of, again, the one way we know how to do it is asking how much of this PSF contamination changes your cosmology. We have one plot in DS showing it. These two are new. I think they've never done it, but kind of lesson is it's not a lot. You might question if that is a lot. We can look into that, but in general, it's not a huge effect at the level of stage 3. And I think, yeah, it is more important to have these kind of tests that are not just heuristics, but can be quantified into something on cosmology.
But that would be a model dependent, isn't it? Like if you go beyond lambda CDM, then you're gonna have to redo this task. Not the raw statistic, but this one in terms of shifts.
Yes, that is model dependent. It's also this model dependent. So I have decided that I'm going to quantify a PSF model in terms of this 4, which is not necessarily true. It's pretty flexible, but not necessarily true. So yeah.
And the question, so how, I always forget, but like where are the bands of like the maximum acceptable error on these raw statistics defined by the collaborations? Like where,
So,
where?
Yes, so usually people will put a band on this, but that's never really useful because it really doesn't tell you. So HSC has a very large row 0 just because their PSF is better. So this plot on its own does not tell you anything. So people usually like to put a band there just so you have a visual guide of, okay, this is 10% of the cosmic shear signal itself. But even with that, it's not like, it doesn't tell you too much if you don't do the next step. Does that make sense? This is really just purely a quantification of how good your PSF model is, but you could have, I don't know, like the degree in which how your PSF error propagates into shear is method dependent. So some methods propagate more, some methods propagate less. So you can't do it without knowing what the method is. I'm happy to talk more about this if people are.
So just a curiosity, if you go back, so the DS,
Yeah.
So the DS has the worst PSF, the 3, right? But still.
I don't know, like
Does the
you
statistics
can't really see from here who has the worst PSF.
No, the one that you showed the 4 that you.
Oh, you mean the size,
Yeah,
right?
the
So
size.
it's just saying our image quality is
Yes,
worse.
image quality.
It doesn't necessarily mean our ability to correct for it is worse.
Perfect.
So you can have the world's worst PSF, but if you know how to correct it 100%, you're still good. Okay. Okay. So right. So we did all this. It was a lot of work. We learned a lot of things. So point 1, we always learn something when we redo something. I think that's not new to everyone. And I think maybe what we add here is at this stage of LSST, we're just trying to figure out what the data is doing. It could be useful to do some of these earlier steps and not just the cosmology part. It's very important to document. So we spend way too much time looking for code in somebody's private repo and whatnot. So documenting is important, and what Scott mentioned, these main metadata that people just don't usually store anywhere. is if we are ever going to use them for something important, we should actually store them and document them. And the last point is this kind of sort of philosophical point of a lot of these pass fills are a little vague, and you could just have one thing that doesn't pass, but everything else looks fine. Are you just going to stop the analysis and say we fix it until we fix it? That doesn't seem like the sustainable way of doing it. So yeah, so I think the connection to cosmology is a bit weak. So a lot of these tests, I think, should be taken on a whole to determine whether your catalog is ready. And also what I think Vivian mentioned, we keep coming up with tests, but at some point we're just testing the same thing. And really it could just perhaps be useful to find like 3 things that we think absolutely useful and informative and just do those. I'm not advocating for 3, but I'm just saying like, it's time to revisit the things we do and think about it more deeply. Yes.
This is probably a very naive question, but like, are the results of this kind of tests for the sheer catalogs then informative to test for systematics and work for the pipelining the analysis for those original systematics at the 2-point level statistics? Or when you compute the 2-point correlation function?
Yeah. So I think this is a direct 2-point test. And I think, right, so you can look at this. I think the problem with a 2-point test, you can see something and then think, okay, maybe my PSF is a function of, maybe my shear is actually a function of signal to the galaxy. So like, you can go back and look at these. So it's like information you can go back and look at to support your argument, but them on themselves, it's hard to directly say this is going to do that.
Okay.
Yeah. So I think that, like, it's important to do all these things for the sake of that argument, but it's hard to put a criteria on. Okay.
I have one more question.
Yeah.
So I think that's gonna be especially important for stage 4, my question. So if we come up with more and more tests, and these tests are more and more stringent, then we're gonna cut more and more galaxies. And at some point, the cuts will bias the cosmology themselves, because you have such a small sample, and these tests can, accept more one type of galaxy than other ones that can also affect cosmology. Do we simulate this? Do we know these effects? Because in supernova, they simulate these effects very well.
So I think in reality, that doesn't happen. And the things we cut out are usually kind of weird stuff. I wouldn't worry about the LSST stage. We don't have enough galaxies. There are things like, so there are established way you can correct for the bias because of selection. So that is fine. If we cut on signal noise, if we cut on size, we can calibrate that out because there is a bias, as you pointed out. But like a lot of the things that DS uses these tests to cut things are, I don't know, like very faint, very blue, very big objects that just don't, like, they probably don't do anything to the cosmology, but they show up weird on these plots. Does that make sense? Okay, any other questions?
Can you go back to the previous slide? What is the plus? What are you wearing there?
What am I?
Yeah, the plus 2 sigma and the minus 2 sigma.
Oh, sorry. Yeah, it's okay. So it's okay. So the delta PSF model, right? So you can quantify it this way. So there is a procedure in which you can get what alpha, eta. Oh, sorry, that's beta. Alpha, beta, eta are. And then that can give you kind of templates of PSF errors. So you can draw a lot of them and take 1 plus 2 6. Okay. Okay. Yeah.
So I was wondering, is there a way for people to quantify how the errors do to the PSF compared with theoretical errors coming from covariances, or is there a way to see
The relative.
the relative error?
Yeah, I guess like you can sort of do this, right? So
I
you
can
can
see
you
that
can do it wrong
Like in the validation process without.
without going to
without going
cosmology.
into-
So I guess yeah. So the step before going to the constraints is we came up with kind of bounds on the PSF error propagation into the 2-point function of shear. So you can compare that to just the covariance, right? The statistical error bar. So there are things like that you can do. Yeah.
I don't know which one was been on this, but are you gonna? The HSC is much like LSST, but so if you go back to those plots, did you learn anything that will help us make selections for LSST? Looking at the HSC, like there was one plot where you said it cuts on that method of one.
Yeah, I don't think that's,
This one, you said that they cut on very high signal to noise.
we put on high signal and kind of high size. I mean, I think that's, I guess it would be interesting if we don't cut there and see if they passes everything. The reason they cut there is because of blending.
But what's the difference?
Sorry.
Isn't LSST and basically the exact same?
Yeah. So I think we learned from here that LSST will have that problem. And I don't have a solution. Yeah, like, yeah, HSC is LSST depth. So LSST will have that problem. I think people know that. I don't.
Does that mean that projections for like the number of galaxies per square, whether the blue using LSST or wildly optimistic or something?
Not like, there was some very simplistic blending account in there. But yeah, because like the simplistic blending account would be, okay, I can't have neighbors within some radius. I cut it, right? But really the effective blending is not that. The effective blending is every photometry is blended. So I think that, I mean, people are doing it, like doing some analysis on it, but I don't think it's a solved problem. Yeah, so I think if we don't account for blending, the LSST numbers should have been a lot higher. Because this number, the HSC number, was pretty close to the LSST kind of expected number. Okay, I'm gonna move to the next thing. Happy to talk more if people want. Okay, so the next thing I'm going to talk about is this whole new data set you probably never heard about called Decade. Decade stands for DCAM all data everywhere. So it is a data set that initially was compiled for near field cosmology, so finding dwarfs. But a group of us decided maybe it can do far field cosmology too. So we tried to do that. All credit goes to Daya, who's a grad student at Chicago, who did most of this work. Yeah, so the lesson I'm trying to get from this exercise is, okay, so this survey was not designed for lensing, right? So it's just data sitting there. So the question is, how bad a data set can we tolerate? So it kind of goes in the other direction to do cosmology. Okay, so as I said, we actually have a lot more data than the three main stage 3 data sets. The community has been just taking data nonstop and they're just everywhere. So maybe we can do something about it. So this particular data set, Decade, has a few features that are particularly interesting for the sake of preparing for LSST. It is on a different part of the sky than DES, but it uses a very similar processing pipeline. So we can find if SA is different on the other part of the sky. Very good. It forces us to stress test our tool because this data set was not designed for lensing, so it's relatively patchy. The depth variation is huge. And if you combine with DES, you actually mostly get LSST coverage, so that's interesting. And this is related to the third point. If we can actually use this data to do cosmology, does that mean that a lot of our requirements on these lensing cuts should be a bit relaxed? So yeah, so this is why this is interesting. I'm going to play a movie, not a movie, but a kind of a snapshot of where we got here. So the first part is just DES. So a lot of you could probably recognize things. So DES data over the years, this is credit Alex Wagner. This is before we started. This is what? Everybody shout. What is that patch? Nobody really knows what that patch is. Scott, sorry? What's SV? Nobody remembers SV? I'm disappointed. Okay, this is year 1. Year one, okay, very good. This is year three. We cover the whole footprint, but slightly patchy. This is year six. Okay, so this DS, 2019, we've done year six observing. This is what is going to our year six cosmology. But you notice there's a lot of stuff outside as well. People have been just taking data, doing other stuff. Similar surveys, a lot of it is decals, you probably know that. But there's also a lot of cluster fields, people finding white dwarfs, stuff. Okay, so this is when Delft came in and say, okay, let's just patch it up and do a survey proper to find dwarfs. Okay, so this is when DS finished. They filled it in, Okay, so this is the end of the data we're going to use for Decade or Delft. So you can see it's pretty good, right? We filled in almost LSST. And it's not very deep, but we have 4 fields we can do for those and that's really all we need. Okay, so this is the data we took to do this Decade Cosmic Shear project. This is all the people that's involved, mostly Chicago-based. So Alex and I wrote the initial proposal. These 2 grad students did most of the work. There's a bunch of undergrads and postdocs that came in and out. Robert and Monica, really big thanks to them doing the kind of the processing, which is like probably most of the work. So making the initial images, single exposures into coads and doing that processing. Okay, so that's what we end up with. That's a shear catalog number of galaxies per unit square. And then you can see the relative locations. So DES is on the other side of the galaxy. That's DES in the strange projection. And these are HSC ankits. Okay. Okay, so the goal of this project is to make a shear catalog. So make the coad data from Decade, generate, calibrate, test a shear catalog, generate, calibrate, and test a photo Z catalog, full photo Z distribution, and then do cosmology. And to see if we can, just like zero order, if we can do it at all, because this data set was not meant to do this. Okay, so we did everything I talked about in the previous project. So we did all the tests. Nothing too shocking to see here. I think that the color dependence, this plot was not in the previous project. This trend is also seen by DES. It could be real. It's some color dependent PSF thing. Okay, so here are the numbers. We end up with 107 million galaxies, 5,400 square degrees, a bit shallower and a bit wider than DS year 3, and like shallower than year 6.
Well, what did you use to measure shear?
Medi-cal. So we're most comparable with year 3. Year 6 is Meditech.
They're not worried about how to correct or how do you account for the correlation that you just
pointed out. I think we did some tests to convince ourselves this is not huge for our statistical, and then year 6 season the same thing too. This has been an interesting exercise because we're sort of in parallel with year 6, so we're just finding each other's problems and like yeah, just helping each other out. Okay. Okay, so we did photo Z's, they look reasonable. I think the thing I'll point out is we use kind of the same analysis, kind of SOM-PC pipeline, and we compared with clustering redshift using BOS and stuff. So this is all kind of consistent with DS methodology. The redshift is a bit lower as expected because we don't go as deep. One thing you might worry about is the covariance, right? So the galaxies are quite inhomogeneous. This plot exaggerates a little bit, but it's not super far off. You can't see very well, but there's like a grid over here. It's like focal plane size grids. Somebody was looking for a white dwarf. And yeah, that part goes very deep. There are patches that have like 1,000 exposures and fine. Like to the extent that Medi-cal doesn't finish. So we had to throw away stuff because Medi-cal just didn't finish. Okay, so yeah, so this data set, you might worry the covariance if we just do a simple kind of Gaussian covariance with mask correction, you won't get it right. But turns out the effect is actually not that big. Maybe it averages out in the scales we care about. So this is looking at kind of just on simulations, whether the covariance of a randomly distributed field versus a kind of an inhomogeneously distributed field give you a different covariance. So that was actually a big relief. We didn't think that was gonna work. This is another really cool thing that we were never able to do in DES, mostly just because there are too many groups working on this, which is taking your footprint and splitting it. So splitting it into high air mass, low air mass, high seeing, low seeing, high exposure time, low exposure time, so on. So why is it hard? It's hard because you need to recalibrate everything. You need to recalibrate your shear and redshift in each of these, and that takes a lot of time. But since I was doing everything, it was easy for him to do. So anyway, so point being, these splits sort of give you a sense of how important this inhomogeneity is. And we set ourselves like a 3 sigma threshold, so none of these are like really failing, but you can see trends of things here and there. I think mostly I want to point out this on itself is an interesting kind of thing that we couldn't do in DES. And it's related to things like sometimes you take the DS data and you want to do a different sample, but people tell you, no, you can't do that because the calibration is different, the redshift is different, or whatever's different. So that's kind of annoying. So it feels like we should be able to release a catalog that you can do your own calibration. So this is kind of one step towards doing that. Okay.
So why the calibration change with
The sample, because the sample is usually on, sorry, the calibration is on the whole sample. So basically, we have one, how do I say? Okay, so we measure ellipticity and we need to calibrate it, multiply it by one number, this sample, to get our catalog. And so if you take these 100 galaxies and derive that one factor, versus if you take these 100 galaxies and derive that factor, just from the data itself, it will be slightly different because it's derived from the data. Maybe that's a question. So it is signal noise and size dependent, for example, like it depends on the sample.
What happens if you use the same calibration?
So you would probably get things slightly off. Yeah, so yeah, if the characteristics of the galaxies are not very different, you're probably okay. If you're like systematically getting a high signal noise sample, then you'll probably get it off. And this is related to how we do calibration in DES.
Yeah, because if you calibrate all the samples, and
okay.
each galaxy is calibrated or whatever, I mean, I thought that, calibration is to correct something that now you correct is fine, so you can divide after calibration, I guess.
So because the calibration is on the sample, I think that's the problem. We're not doing object by object calibration.
Okay.
And the same for, don't post this on Twitter.
I thought that 0.5 is important.
Yeah, for example, for this, right? So this is the redshift distribution of the sample. So if you took half of the sample, you need to rederive this. It's not very, I mean, it's not hard. It's just like a whole thing you need to retreat again. The actual procedure is not hard. It's just tedious. We can talk about it more.
Just what if you are using with the calibration interpretation works when you correct rate like over the whole average. You have to average over the whole sample. Which was what she said about correcting the number. This is how we know the average. So for down how the correction you have to average over the whole.
Okay, so
There's a number that comes
Yes.
of the average of it, but it is meta calibration specific. So other methods may not need to be so much work. Yeah, I mean, again, I can go into more. There's other things like image simulations. So a lot of these rely on image simulations. And we spend a lot of time making the simulations look exactly like the data. If you now generally take half of the data, you need to also adjust the simulations to look like half of the data. So it's just, again, tedious, not hard, just tedious.
Can I ask a question?
Yeah.
About don't you worry about the when how do you do if you have different variations? Again, that you
Yeah.
have resonance that depends also on the position.
Say
Or
it
not.
again.
So if you have a change on the depth,
Yeah.
you would again your precision will also depend on the location.
So that we did not account, that effect we are worried about.
Okay.
So we were hoping tests like this would reveal something. If it's like half of your footprint is systematically at a higher redshift than a lower redshift, they shouldn't get like the same if you use I guess you should get the right cosmology if you do it right. So then it's not, okay, so what is the problem with having spatially dependent NFC is only if that structure mimics cosmology, right? Right, so I think, yeah, so we didn't test that, but we were hoping this could give us this.
I have a question. So your survey depth, it's dependent on where you point because you don't show the data. But what about the filter coverage? Like, do you always observe in all the filters that you observe in the main survey, or there's some areas that you just observe with 1, 2 filters and so on?
We always require all 4 filters because we need to do vertices. But you're right, the fraction of each survey is not homogeneous. So we didn't actually look at that. That's a good one we can think about. Yeah.
What is DCR?
Differential chromatic refraction. So this is the thing. Sorry, I just put it up there. Most of the questions. Sorry. So it's like when you look at like more air mass, both the position of that object is shifted and that it has an elongation towards the zenith. So it's just because how, diffraction from the atmosphere works. So at high air mass, it's a bigger. So why is this a problem? It's a problem because it's chromatic. So it is a color dependent thing. So the thing, okay. Tell me if I'm taking too much of time explaining these things. So the worry is that your PSF and your galaxy actually don't have the same color. And if the PSF, like both of these are color dependent, then you're always correcting with a slightly wrong PSF. And DCR is one of the effects that this is known to be bad.
So for the previous, because now you're trying to do this for like this extended data set.
Yeah.
But for
Why is it not a problem for the others?
the others,
So
that
they-
they take into account?
Yeah, so the reason why we're particularly worried about it is because we're using data that is past the DES criteria for air mass. So we're using higher air mass data. So this effect will be in DS2 and they checked for it too. They didn't do that exact test, but they would check some things about it. But because our data is particularly bad, we want to spend extra time looking at it. Yeah. And this is like, again, it's kind of, there's implications, right? So LSST, when we decide the footprint, there's always some air mass kind of cut. So yeah, if we demonstrate we can actually deal with it, then perhaps it's a indication that we can push more to worse conditions.
Have never heard of air mass.
Air mass?
But I was about to say, Irma is like it's related to the.
Okay, sorry, I may need to explain what air mass is.
No.
Sorry, yeah.
Yeah.
Okay, so it's just like, okay, so this is Earth. This is the atmosphere. So looking through here and looking through here, you're looking through different amount of air.
I know, but
Okay.
but what I'm trying to say is this is the observation of 1 year. You're not observing the same galaxy with the same air mass all the time.
Yeah, so this is mean air mass over like whatever time this is over the exposure. Like mean air mass
Also,
also.
the sky at different position. and
Yeah, yeah.
You know, these are have different air mass.
Yes, except for because how DS observing is, it's always like, if you look at the air mass distribution on this one, it's a gradient. Just because it's in Chile and it always looks at that part of the sky in this certain way.
Some part of the sky is always.
Yeah. So declination is just air mass, basically. LSST, I don't know if it'll be the same. I think because they rotate the thing, maybe it's gonna be slightly different.
Again, the flows of how it changes.
Yeah, so these are just quantities of, okay, the RA error because of DCR, the DEC error because of DCR, the E1 error. These are just maps that DS splits out. Like, we just use them.
So for example, in the second one, and the air mass, so then it's showing that
So if
So
I,
what did you change? You changed, what did you change? So it shifts.
so I split the sky into half of it being higher air mass, half of it being lower air mass, and do cosmology in the two parts.
Okay.
So in the higher air mass part, this is how much it shifts relative to fiducial. Yeah. Cool.
Yeah, so I understand the deviation from the previous flow is not significant,
Yeah.
but there is a correlation between the two last columns, right? But it should
The
be there,
two,
the
what-
omega and sigma 8. Whenever
Yeah.
one data is shifted to shifted in omega, the same data is shifted in the sigma column as well. See, if you pick
What's
the
going in
fifth
one
one,
direction, generous.
sorry?
They're correlated.
Oh, yeah.
Yeah, it's because it should be there, right? It's because the
Yeah.
S8 is not, so it's.
That's it, it's not.
So S8 is this direction. So yeah, so mostly we just care about S8, but yeah, the others.
Yeah, that's so because I didn't have time to look, so I asked people to come back, so it should be there. It's coming.
Yeah, they should. Okay, cool. What times? Yeah.
Yeah, it was just to clarify to myself, I think. So each of the regions that is spatial in one unities will have different number of objects, different LC,
Yeah.
different,
So that we need to
different
redo.
variants that you
Yeah.
have to do for each of them.
Yeah. And that's why it's kind of annoying.
I think we're having discussions, right?
Yeah, no, I actually don't have that much left, but it's okay. Yeah, we're just bleeding into discussion.
This is discussion.
Okay.
Blending into discussion.
Okay, so yeah, so last thing I do is say, like, this is a forecast, but we recently have unblinded. I can't tell you what it is, but it's not, S8 is not 1 nor 0.1. So it's not in between.
Thanks, Julie.
Yeah, no problem. But yeah, like expect results first. I didn't want to show it because we're still like, I literally I'm blinded, like,
Otherwise, Scott will take a picture.
yes, that's a good tweet. Yeah. Anyway, okay, some takeaways from this analysis. So the DS method seems to work on this data to the precision level that we care about. Like, note that here, the error bars are not as good as year 3. Year 3 did add shear ratio, so it's a little hard to compare, but it's like not the tightest country ever. So saying it works to this level maybe is not a direct statement of LSST, but at least we have ways to deal with it. Decade gave us a unique tool to perform these studies where survey inhomogeneity does what it does to each step of the survey, and that has been very valuable because we keep having these questions in LSST, like what's going to happen if we do rolling cadence or whatever. And this is a data set that exists there for us to test. Okay, yeah, and then we can combine with year 3 to basically get 10,000 square degrees. I just want to show that we actually have more data. So the thing I did show was part of this and part of this. That was the decade data set. You can see the more homogeneous DES footprint there. But we actually have data around DES too. That's taken, that's measured. We haven't looked into it yet. But in principle, while we're finishing DES and LSST not here yet, we could also process that data and do some cosmology. This is in terms of depth, so you can see the different depth. And this is interesting, right? You actually are deeper here outside DES in the LMC region because everybody's looking at there. Yeah.
So you're not planning to do 3 times 2 with this?
We thought of we probably will if we can find people, but lenses are actually going to be harder here because they're like homogeneity and stuff. Okay, I won't talk about this because Scott talked a lot about it. Mostly just like we actually measure maps, but we decided this is the thing we do, meaning this is a huge reduction of information and we should try to get the information back. There's a bunch of papers out there that do higher order statistics. Read up on that. This is akin to the field level inference thing Scott talked about. Some work done by Yuki, Justine, Francois Lanus, and myself. So yeah, again, very similar to what Scott was talking about using a particle mesh kind of differentiable simulation thing. So going back to the discussion this morning, we could get it to work, but only in like this big of a sky and then like very coarse resolution. So there's a lot of work to do in terms of high dimensional sampling, I think, to make this even remotely.
Can you just explain a little bit what's going on?
Yeah, sorry. Okay, so field level, Scott explained it perfectly. We basically have a lensing map. Okay, so this is what we need for, okay, so convergence map. Okay, so you have a 5 by 5 square degree convergence map. And what you want to do is you want to simulate, Fourier simulate a bunch of maps that are consistent with that map. And hopefully they will map out some contour. Okay, so the novel thing here is like you're simulating it from the initial condition. Okay, you're simulating it from redshift, whatever, like 10 or like 20. So you do some kind of initial simulation, initial condition there, you forward evolve it, just like an n-body simulation.
So there's a grid of cosmological parameters.
It's a sampling thing. So what you want is to, so this is the HMC thing that you heard this morning, is to go towards the more likely point. Yeah, so, but the novel thing is the model is this end-to-end from initial condition to map the whole thing. Yeah.
Do you also marginalize over initial conditions?
And yeah, and so our initial, like what we're stuck right now is it's really hard to fully sample over initial conditions. So the counter is always artificially tight. So yeah, so that's something we're working on.
Do this, you do the Born approximation, you do an n-body simulation,
And then born it,
and
yeah.
then you use kappa and shells.
Yep.
So you're not doing ray tracing.
No.
Um,
Yeah. Yeah, I need a differential ray trace. Is Alan doing ray tracing?
Yes,
Okay.
I mean, for the 2-point stuff, it doesn't matter, but.
Yeah. Yeah.
But it's impossible. Maybe you can only get flat Foursquare.
Yay! It's yeah, I mean, yeah, I think it's just really cool, right, to see these things. But also, like, why do we need this whole thing? Yeah, I think I constantly ask myself, like, we can SPI this so easily. Why are we doing it? Okay. I just want to point out, okay, so why are we doing this? The hope is that we can also look at new physics, right? If we're just doing lambda CDM, perhaps there's no point doing that. But like maybe there is some exotic physics that only shows up in this particular way. This is a paper again by Daya showing that using lensing to get primordial non-Gaussianity, and upshot is in some of the configurations, some of the triangle shapes, LSST or 10 gets pretty close to DESI. So there is information we should use it.
So you draw the initial conditions
The-
from,
This is not that. This is a different analysis.
uh,
Yeah, this is just Fisher. This is not.
but is this using the scale of bias? Or you can say
So this is the Quixote simulation. Add in FNL. So it's not scale dependent. It's the oh,
3-point.
sorry. You're asking what statistics. This is like PDFs of lensing fields.
there's nothing to do with it.
Nothing to.
I mean,
Yeah, this is just like, I just want to point out we should do something beyond that. Okay, looking ahead, we're gonna get data. There's gonna be more data. So yeah, I just want to point out like outside Ruben, DESI is almost done. They're gonna extend it. There's gonna be DESI 2. Euclid basically started. I think there might be somebody who can comment on that. Spherics is gonna start like when?
They're launching in February.
Launching in February, so that's happening. And Romans 26, 27, right? So yeah, so lots happening. Something to play with. Okay, just to summarize, Ruben commissioning has started and things are going well, so that's good. Desk is doing stuff to prepare for LSST. And the current configuration is 3x2 plus clusters, and we're semi-organized. We learned a huge amount of precursor data set, and I think this is, for me, I feel like this is the most valuable thing we need to carry forward. And the last point is just like, it is possible that we're not doing 3x2.9 clusters at all when LSST starts. So we should be open to that. Okay, I think that's all. Thanks.
I think we are already,
Okay, we're
we already started.
discussion.
So it's really format free,